Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to talk on the module Junction Field Effect Transistor JFET and MESFET from the paper Electronics. So let us see what we are going to learn in this module. First, we will study the schematic of N-channel JFET. Second, we will discuss about the IV characteristics of JFET. And we will derive the IV relationship for JFET also. Lastly, the metal-semiconductor field effect transistor, that is MESFET, and the expression for its saturation drain current will be discussed in this module. So students, let us start with a basic introduction about the module. The JFET is one of the simplest transistors from the structural point of view. It is a voltage controlled semiconductor device. In this, the current is carried by only one type of carriers. So it is a unipolar device. It has a very high input electrical resistance. JFET consists of a doped silicon or gallium arsenide bar. There are ohmic contacts, the two ends of the bar and the semiconductor junction on its two sides. If the semiconductor bar is N-type, the two sides of the bar is heavily doped with P-type impurities, and this is known as N-channel JFET. So on the other hand, if the semiconductor bar is P-type and the two sides of the bar is heavily doped with N-type impurities, then this is known as P-channel JFET. So when a voltage is applied between the two ends, a current which is carried by the majority carriers of the bar flows along the length of the bar. There are several terminals in JFET. So the terminal through which majority carrier enter the bar and the terminal through which they leave are known as source and drain respectively. And the heavily doped region on the two sides is known as a gate. So the junction field effect transistor, the junction is reverse biased. As a result, depletion region from which extends to the bar. By changing gate to source voltage, the depletion width can be controlled. So the reflective cross-section area decreased with increasing the reverse bias. So the drain current is a function of the gate to source voltage. Nowadays, JFET is obsolete. Its applications are limited to circuit designing, where it can be used as the amplifier and as a switch both. Junction field effect transistor JFET. So this type of transistor uses the depletion region of one or more reverse biased PN junctions to modulate the cross-sectional area of a semiconducting channel for the transport of charge carriers. Here the current is due to the carriers of one polarity unipolar device. So we have the N-channel JFET if the channel is N-type semiconductor, and we have the P-channel JFET if the channel is P-type semiconductor. Let us first discuss the N-channel JFET. So now this figure shows the N-channel JFET, where we have a thin bar of the N-type semiconductor which is sandwiched between two P plus regions. Channel is N-type which is isolated from P plus regions. Gate by junction depletion regions. So here the channel N type is isolated from the P plus regions or the gate by junction depletion regions. So students, here we have three kinds of electrodes. These are the first is the source, that is the source where the carriers are originated, and it is negative with respect to the drain charge carriers, and they flow from source to drain. Next is the drain, which act as the sink for charge carriers, and this is used for collection. Next is the gate, which is a rectifying junction with the channel. So students, N-channel JFET is always preferred over P-type due to higher mobility. Depletion region is formed between the N-type channel and the P plus region gate, and the width of the depletion region is represented by W between the gate and the channel in equilibrium condition. The voltage which is applied between the drain and the source terminal is VDS, or we can represent it by VD. The drain is at positive potential with respect to the source. The voltage applied between the gate and the source terminal is VGS or VG. It is less than or equal to 0, reverse biased. When VD is greater than 0 is applied, electrons starts flowing from source terminal to drain terminal. Thus, the drain current ID flows from drain to source. So, the flow of charge, that is drain current, is influenced by the application of VGS. Thus, it is known as field effect transistor. Now, the channel width, it varies with VGS and affects the flow of charge carriers. The cross-sectional area of the channel, it is reduced due to reverse bias of the gate, and thus JFET is a voltage controlled resistor which can be varied by varying the voltage VGS. So N channel is uniformly doped with ND, and P plus gate is heavily doped because spread of W on P side it is neglected and it is considered only in the channel. Now consider the case when Vg equal to 0, or we can say Vgs equal to 0. The channel resistance is R naught equal to rho L by A equal to L by Q mu n NdA equal to L by 2Q mu n NdZ multiplied by A minus W naught, where Nd is the donor concentration, W naught is the zero bias depletion region width of upper and lower P plus N junction, mu naught or mu n is the mobility of electrons, Q is its charge, and 2A is the total channel thickness, and 2A minus W is the thickness of the conducting channel at zero bias. So students, cross-sectional area for the current flow is given by A equal to Z multiplied by 2A minus 2W equal to 2Z multiplied by A minus W, where 2 multiplied by A minus W is the thickness of the conducting channel at Vg equal to Vd. So the variation in the channel thickness profiles for Vg equal to 0 and different VD. So the recalling the expression of the width of the depletion region W for the PN junction, it is given by W equal to 2 epsilon s by Q multiplied by 1 by Nd minus Na multiplied by Vi minus Va to the power 1 by 2, where Vi is the built-in potential and Va is the applied bias. So Vbi is the built-in potential at the gate junction when Vg equal to Vd equal to 0 and the depletion width is constant throughout the channel, which is equal to W naught equal to 2 epsilon s by Qnd to the power half multiplied by Vbi. Let us now discuss about the IV characteristics of JFET. So consider the symmetric structure model, that is linear change in depletion region across the channel. Consider Vg equal to 0. Let us first consider the case 1, that is linear region. Vd is small and it is positive. So if a small Vd greater than 0 is applied less than Vbi, gate to channel junction is slightly reverse biased and results in a small depletion width approximately equal to Vd by R. So a small drain current Id flows which varies linearly with applied Vd, and Id is approximately Vd by R0, where R0 has been previously explained, which is nothing but the channel resistance. So the case 2 is the nonlinear region. When Vd increases moderately, the voltage across the channel increases from 0 at the source to Vd at the drain. Gate junction becomes increasingly reversed bias from source to drain because as Vd increases, the depletion width W increases and average area decreases for the current flow. Therefore, channel resistance increases and current increases at a slower rate. Thus, rate of increase in Id with Vd increases is nonlinear with increase in Vd. So if Vx is the voltage at the distance x from the source, depletion region width Wx becomes W equal to 2 epsilon s by Qnd multiplied by Vbi plus Vx to the power 1 by 2. Here Vx is reverse biased with respect to the gate, Vg equal to 0. So Vx has maximum value Vd at the drain and hence W is maximum there. So the elemental resistance dr associated with the finite length dx of the channel, it is given by dr equal to dx by 2q mu n nd z multiplied by a minus w. Total resistance of the channel will be R equal to integral 0 to L dr. Since W is greater than W naught at all the x except x equal to 0, R is greater than R naught. Therefore, R increases with increase in Vd. Hence, Id falls below the initial linear resistance line and increases slowly. Let us now discuss the another case, that is pinch-off condition when Vd equal to Vd saturation. As Vd is further increased, the gate to channel width W increases further. At Vd equal to Vd saturation, two depletion regions touch each other at the drain, that is W equal to A at the drain, which is shown in this figure. So for an abrupt P plus N junction, drain voltage Vd equal to Vd saturation can be obtained from equation 3 after putting Wx equal to A. So we get A equal to 2 epsilon S by Qnd multiplied by Vbi plus Vd saturation to the power half. Vd saturation equal to Qnd by 2 epsilon S A square minus Vbi. At Vd saturation, source and drain are pinched off or completely separated by a reverse biased depletion region. Source and drain are isolated from each other by the depletion region, and the channel conductance becomes zero. So here, large current ID saturation can flow across the depletion region, which is similar to the injected carriers into the reverse bias depletion region, such as collector-based depletion region of BJT. So the current flowing through pinched-off region to the pinch-off point is limited by the number of electrons that are injected from the tip or the source of the channel. Let us now discuss the another case, that is the saturation region, where Vd is greater than Vd saturation. When Vd is greater than Vd saturation, beyond pinch-off, the depletion region near the drain expand and the drain is isolated from the source by the depletion region. So, ID is approximately equal to ID saturation and is independent of Vd. So practically all additional voltage appears across the depletion region. Now when some Vg is applied, that is less than 0. So when a reverse bias Vg is applied at the gate, depletion region of P plus N junction becomes wider, W increases, and cross-sectional area of the channel A is reduced. So for small Vd, the channel behaves as a resistor, but its resistance will be higher because area available for the current flow reduces due to Vg. Hence, Id reduces in comparison to the value of Id at Vg equal to 0. So Vd saturation needed for the pinch-off condition decreases with increase in the magnitude of minus Vg, which is shown in this figure. Let us now discuss about the IV relationship. Consider JFET with Vd less than Vd saturation and Vg less than equal to 0. The voltage drop across an element dx of the channel is dV equal to id dr equal to id dx by 2q mu n nd z multiplied by a minus w. So the drain current induced is independent of x. So from this equation, id multiplied by dx equal to 2q mu n nd z multiplied by a minus w, where dr is the small resistance of the element, mu n is electron mobility, nd is doping concentration in the n-type semiconductor, z is the depth of the channel, 2a is channel width, and W is the width of the depletion region at X. And W, which we have already calculated, that it is 2 epsilon S by QND multiplied by VBI minus VG plus Vx whole to the power 1 by 2. So we can differentiate it with respect to V, and we get the expression for dV equal to QND by epsilon S W multiplied by dW. Now putting the value of dV in equation 10 and integrating from x equal to 0 to L and W equal to W1 to W2, where W1 is on source side and W2 is on drain side. Then we get ID integral 0 to L dx equal to integral W1 to W2 2q mu n d nd z a minus W multiplied by qnd by epsilon s W dW. So finally we'll get ID to be equal to q square mu n nd square z by epsilon s L multiplied by A multiplied by W2 square minus W1 square minus 2 multiplied by W2 cube minus W1 cube divided by 3. Now putting the values of W1 and W2 and expanding by the Taylor expansion, we get ID to be equal to q square mu n nd square z by epsilon s L, the whole multiplied by 2a epsilon s q n d multiplied by VBI minus VG plus VD minus 2a epsilon s q n d multiplied by VBI minus VG minus 2 by 3 multiplied by 2a epsilon s by QND multiplied by VBI minus VG plus VD to the power 3 by 2 plus 2 by 3 multiplied by 2a epsilon s by QND multiplied by VBI minus VG to the power 3 by 2. Saturation region. So ID in saturation region can be obtained at pinch off by putting VD equal to VD saturation from equation 8 to 11 and setting Vp equal to Vt saturation minus Vg plus Vbi. So ID equal to Ip multiplied by Vp plus Vg minus Vbi divided by Vp minus 2 by 3 multiplied by Vp by Vg to the power of 3 by 2 plus 2 by 3 multiplied by Vbi minus Vg by Vp to the power 3 by 2. So this is equal to Ip multiplied by 1 minus Vbi minus Vg by Vp minus 2 by 3 plus 2 by 3 multiplied by Vbi minus Vg by Vp to the power 3 by 2. So this is equal to Ip multiplied by 1 by 3 minus Vbi minus Vg by Vp plus 2 by 3 multiplied by Vbi minus Vg by Vp to the power 3 by 2. The ID is independent of Vd and channel conductance is 0 in saturation region. So trans conductance, it is Gm equal to del ID by del Vg equal to Ip by Vp multiplied by 1 minus Vbi minus Vg by Vi to the power 3 by 2. So this is equal to 2 epsilon q mu nd divided by L multiplied by 1 minus Vbi minus Vg by Vp to the power 3 by 2. So Gm in saturation region, it is equal to Gd in linear region. So let us now discuss about the linear region, that is Vd is less than Vbi minus Vg. So expanding the terms of equation 11 and having Vd in binomial series and retaining the first two terms, we get Id is approximately Ip by Vp multiplied by 1 minus Vbi minus Vg divided by Vp to the power half, this whole multiplied by Vd. So the channel conductance or drain conductance is given by GD equal to del ID by del VD for VG constant equal to IP by VP multiplied by 1 minus VBI minus VG by VP to the power half. Therefore, as VG increases, GD decreases until finally at pinch of voltage VP, where conductance becomes 0. Another parameter of JFET is transconductance, which is GM, and it is equal to del ID by del VG at VD constant. And in the linear region, this is equal to IP by 2VP square multiplied by 1 minus VBI minus VG by VP to the power minus half multiplied by VD. So for fixed VD, ID decreases with VG more negative, and ID equal to 0, JFET is turned off at a particular negative value of VG, known as turned off or a threshold voltage. So now if we put VG equal to VTH and ID equal to 0 in equation 13, we get VTH equal to VPI minus VP, that is VTH equal to minus VP. MESFET, Metal-Semiconductor Field Effect Transistor. Since Ft of JFET could increase either with increase in mu or decrease in L, both these features are feasible to incorporate in MESFET. Since metal gate can be deposited in small length in MESFET instead of diffusing the impurities in gate. So for JFET, relatively very small L can be achieved in MESFET. Hence, MESFET are useful for high-speed switching applications, and it consists of N-type conducting channel between a drain and a source. So charge carriers flows through this channel, which is controlled by a Schottky metal gate. So thickness of the conducting channel is controlled by variation in the depletion region underneath the metal gate with applied bias. Hence, this can vary the current between the source and the drain can be controlled. So, MESFET is fabricated by using epitaxial layers on semi-insulating substrate to minimize the parasitic capacitances. So, depending upon the variation in the width of the channel, the thickness of the functional layer, and the Schottky depletion region between channel and the semi-insulating substrate, the MESFET can be divided into two modes. First is the depletion mode, which is normally on. In this case, the width of the Schottky depletion region is less than the width of the channel, VG equal to 0, and in equilibrium condition, the channel is on. So reverse bias through VG can be applied to completely cut off the channel, similar to that in JFET. Next one is the enhancement mode, which is normally off. In this case, the width of the Schottky depletion region is greater than the width of the channel. Already pinch-off condition exists and the entire channel is depleted off. So forward bias is required to allow the flow of current by reducing the depletion region and opening the channel. So basic IV characteristics of both the devices are similar, and both the devices can be made by depositing epitaxial layer of N-type gallium arsenide by MBE. So let us now derive the expression for ID saturation for MESFET. No current ID equal to 0 at VG equal to 0 and ID greater than 0 and for VG greater than VT, where VT is the threshold voltage which is given by VBI minus VP. So near threshold, the drain current in the saturation region can be obtained by putting VBI, as in the VD ID saturation becomes IP by 2 multiplied by 1 by 3 minus VBI minus VG by VP plus 2 by 3 multiplied by VBI minus VG by VP to the power 3 by 2. So we'll get this expression by putting VPI as VT plus VP. Now here we divide IP by 2 to account for the upper channel in MESFET in comparison to that in JFET. Under assumption that Vg minus Vt by Vp is very much less than 1, we have ID saturation equal to IP by 2 multiplied by 1 by 3 minus 1 minus Vg minus Vt by P plus 2 by 3 multiplied by 1 minus Vg minus Vt by P to the power 3 by 2. So using Taylor series expansion and doing the simplification, we get ID saturation is approximately equal to IP by 2 Vp square multiplied by 1 by 4 Vg minus Vt the whole square. Putting the value of IP and 1 by Vp square, we get IP equal to Z mu n q square Nd square A cube by epsilon s L, and ID saturation equal to Z mu n epsilon s by 2AL multiplied by Vg minus Vt the whole square. So students, let us now summarize what we have learnt in this module. Firstly, we studied the schematic of N-channel JFET. Secondly, the IV characteristics of JFET were described in detail. Next, we also derived the IV relationship for junction field effect transistor. Lastly, the MESFET, metal-semiconductor field effect transistor, and the expression for its saturation drain current, they were also discussed in detail. Thank you.